High buildings, long roads, huge bridges. We build the future, but at what cost? The high demand of concrete in the industry has negatively affected the environment through global warming.
But of course, we should not remain stuck in this harmful practice. That's why as the world evolves and time moves forward, different innovations in concrete production are being developed around the world in order to minimize its negative impacts. Basically, the goal is to promote sustainability.
With the mission of developing an innovative product, we critically engineered a concrete mixture that cares for our environment. Not only is strong, durable, and resilient, but also designed for a lighter footprint.
The concrete mixtures for the base case scenario and alternative case scenario are based on ACI 211 mix design method. The goal strength of these mixtures is 43 megapascals. For the ACS, two mixtures are tested first, one with cementoplasm of 40% fly ash and one with 38% fly ash and 2% silica fume. The supplementary cementitious materials are selected based on their effect on the environment and on the properties of concrete. The three SCMs reduce the greenhouse gases emitted and fossil fuel consumed when applied to concrete. The aggregates generally cause low risk on the environmental factors. The Portland cement, however, has high impact on global warming and fossil fuel depletion, moderate risk on carcinogenic and ecotoxicity, and minor effect on ozone depletion.
The team wants to optimize a mix containing the SEM shown while considering their effects on both durability and environmental impact. In terms of durability, it was found that silica fume produced the most durable concrete even at a low replacement percentage, followed by fly ash and then slag. In terms of environmental impact, fly ash produced the most eco-friendly concrete while silica fume yielded negative results. Again, we want a mix that balances both durability and environmental impact reduction. As a recap, fly ash was the most eco-friendly, while silica fume was the most harmful but produced the most durable concrete. Slag had the same trend as fly ash, but less in both parameters. Also, slag involves waterway transportation, which is impractical since our location mainly uses roads. Given those, the team chose fly ash and silica fume. The team decided to work around fly ash since it was the most friendly, but also added minimal silica fume to capitalize on its high durability. The team identified 4 different mixes, and the plot shows the mix's durability and environmental impacts. All what's left is to determine which mix is the most balanced. We did that by normalizing the values, and upon doing so, we determined mix 2 with 38% fly ash and 2% silica fume as the most optimal design.
This life cycle assessment compares the base case scenario and the alternative case scenario in terms of environmental impact. Both are functionally equivalent, meeting the required standards. The LCA covers from cradle to gate, which means only up to the point where raw material leaves a manufacturing facility, and excludes the end-of-life scenarios. While replacing cement with sustainable alternative, it increases transportation-related emissions. Transportation distances were a key factor, as longer distances contribute to higher emissions. To minimize this, raw materials were sourced from the closest facilities to the batching plant at the University of the Philippines, Diliman, using only road transport. This strategic sourcing helped reduce the environmental impact from transport, supporting the ACS overall sustainability. In the Ecoconcrete calculator results, the ACS mix showed a single score ratio of 17.4% in environmental impact compared to the BCS. Portland cement was the largest contributor to environmental harm, releasing up to 850 kg of carbon dioxide per ton through calcination and high-temperature kilns. It also emits nitrogen oxides, which contribute to the ozone layer breakdown and requires significant fossil fuels. Aggregates added further strain through habitat destruction and erosion. While fly ash can increase carcinogenic risk due to heavy metals, it reduces energy and water use. On the other hand, silica fume lowers pollution and conserves resources. Together, they significantly improve sustainability while maintaining performance. Thus, the team chose a final mix of 38% fly ash and 2% silica fume.
This slide presents the total service life prediction for both the base and alternative mix designs using a Life 365 model. For the base case, It predicted service life up to 11.92 years. On the other hand, alternative K significantly extends the service life to 29.50 years. This graph plots in percentage weight concentration of chlorides at 50 mm depth over time. For the base case, the threshold concentration is reached just before year 6. In contrast, alternative case delays the same threshold until year 23.6. This delay in initiation time is crucial because it defines the first major phase of service life, which is to delay the onset of corrosion as it ensures durability and mix optimization. Lastly, surface chloride concentrations are shown here. Alternative 1 exhibits a higher surface concentration than the base case throughout the time frame. This could be due to increased chloride binding or surface accumulation in the model, but importantly, it does not translate to deeper penetration. The internal resistance provided by SEMs offsets this higher surface load, resulting in a much longer corrosion-free period.
In creating a circular economy, the use of byproducts contributes to promoting such, and through engineering it is possible to not just reduce the environmental impact with respect to ACS but also a balanced consideration on other aspects such as durability. And balancing its impact on all considerations must be done because this is what Ecoconcrete means, and this is what the world needs today: engineered balance.